Okay, so this is the outline of this chapter. The first part is about the Coulombs Law, Coulomb 定律, and then we'll talk about something about the charges quantized. Charges quantized. So you can only count 1 electron, 2 electrons, something like that. And then the last part is about the charges conserved. We cannot create some charge or diminish some charge, so the charge is conserved. Okay, so the first we talk about this one. So whether it is a magic. So here is a simple experiment. Yeah, simple experiment. We have 2 glass rods were each rubbed with a silk cloth, and one was suspended by thread. So you have a 2 glass rod. One is here, one is here. And then one of them is hanging here, so this is a string. Then this glass rod is free to rotate. This one is free to rotate. And then you try to use a skew cloth to rub these two glass rods. Then the phenomenon is like if you put this glass rod close to this hanging one, then when they are close to each other, they repel each other. So this is the first experiment we observe. This is the first phenomenon we observe. And then the other one is, if we change this glass rod to another plastic rod, actually you don't really need to remember, this is glass, this is plastic, or this is steel cloth. You don't need to remember that. I will not ask it in the exam. So actually, for the second one, we change this glass rod into a plastic rod. We still rub it, but we still rub it with fur. We don't rub it with a skew cloth. We rub it with fur. And then we also try to put it close to this hanging glass rod. Of course, we still use skew cloth to rub this glass rod. And when we brought them close together, then the rods attract each other. So they are different. If we rub these two, they will repel each other. If we rub these two, we change one of the glass rod into plastic, then they will attract each other. So this is the different. Then the physician should try to explain why it will be like that. Okay, so they try to explain it like we have 2 polarity of charge. So for the glass, if we warp it with the skew cloth, then there will be positive charge. On this glass rod and also this one. And as much as they have a same polarity of charge, they will repel each other. And for the bottom one, still the glass rod have positive charge, but for the plastic rod, it has a negative charge. So they have opposite polarity, so they will attract each other. Why will be like that? Why this will be positive? Why this is negative? I don't know. It should be something like the chemistry issue, but they only try to explain this phenomenon using the concept of charges, the polarity of charges. Okay, so the 2 charge rods of opposite sign attract each other. So the plus sign indicate the positive net charge, and the minus sign indicate a negative net charge. So this is the highlight particle with the same size of electrical charge repel each other, and particle with opposite sign attract each other. So I think you should learn it in primary school. Okay, so here we talk about the classification of the materials. So in terms of electricity, we will separate the material into these 4 types. So the first one is the conductor. The conductors are material in which a significant number of electrons are free to move. 导体. So conductor is 导体. So yeah, I still think you should have learned it in primary school. Example include metals. And then the second type, the charged particles in non-conductors, or usually you call it the insulator, 绝缘体. Insulator are not free to move. I mean the charge on the insulator are not free to move. They don't have free electrons. For the conductor, it has free electrons. So example include rubber, plastic, glass. Yeah, they are also insulators. And the third type is the semiconductors. Yeah, maybe you should know it in chemistry class because you learn the periodic table. On the left side we have metals, on the right side we have insulator or some gases, and in the middle we will have something like the semiconductor. Yeah, but yeah, usually when you learn chemistry, when you learn the semiconductor, it is up to there. Then you know silicon are some sort of semiconductors, because the characteristics of a semiconductor are really complicated. Yeah, so for ECE students, they will have several courses studying the semiconductors. Like me, we are doing IC chip. So the IC chip, the material for the IC chip are usually the silicon. So we need to learn something like the MOS transistor, how to calculate it, because the characteristics are really non-linear, so it would be difficult to calculate. For the resistor, you should know the Ohm's law, V equals IR, which is a linear relationship, so it will be easy to calculate. But for semiconductor, it has something like the non-linear characteristic. So yeah, when you need to learn about it, it will take much effort to learn about it. So this is the semiconductor, 半导体. Okay, example includes silicon, germanium in computer chips. And then the fourth type is called the superconductor, 超导体. Okay. Superconductor are material that are perfect conductors. Perfect means no resistance, low loss in there. Perfect conductors, allowing charge to move without any hindrance. Without any hindrance, without any resistance. So superconductor are not so we cannot see it very often, because the superconductor phenomenon will occur in very low temperature. Originally they find the superconductor because at that time I don't know the scientists. I think the scientists discovered the liquid helium. Liquid helium. Yeah, you know, helium is the second element in the periodic table, high. So for the liquid helium, the melting point is around 2 Kelvin. I'm not really sure, but around several Kelvin. I'm not sure whether 2 or 3 or 4. I think around 4 Kelvin. I don't really remember. Yeah, around 4 Kelvin. So which is around minus 270 degrees Celsius. So this is a very, very low temperature. But yeah, when they try to put the liquid helium for the circuits, so they suddenly find the superconductor effect. So the resistance suddenly disappeared. So this is the superconductor phenomenon. And later on, the chemistry or the physician try to find some material which can make this temperature having superconductor phenomenon higher and higher, so that it will be easier and easier to have this effect, because yeah, this material doesn't have any resistance, which is quite good. They doesn't have any power loss there, so it's good. But yeah, it's difficult to have this phenomenon to occur. Anyway, just know there are these several types. Mainly in this semester, we only need to know the first two, still like what you have learned in primary school or high school. Okay, so charged particles, the property of conductor and insulator are due to the structure of the electrical nature of atoms. So atoms consist of positive charged protons. So protons, we have neutrons, we also have electrons. We also have electrons. So in high school, I think in chemistry class, you already know for an atom, maybe a hydrogen atom. So you have hydrogen may not be too good, maybe a larger one. So you will have a proton and neutrons in between. So this is called the nuclear. So this one is a positive charge. For a proton, the charge is a positive E. Each proton has a positive E charge. And for an electron, we have same amount of charge, which is appear as the electrons, and then it will rotate around the nucleus, so that the whole atom should be electrically neutral. So they have same amount of positive charge. So this is charge, positive charge. For the neutron, 中子, it doesn't have any charge. It is electrically neutral. But for the overall atom, it should have it should have a zero charge there. Yeah, of course there will be something called the iron, or they may lose an electron or have one more electron. Then there may be charges. But this is something like the chemistry problem, which will not be discussed here. Okay, so the proton neutrons are packed tightly together in a central nucleus and do not move. Okay, so for the conductor, like copper, so come together from the solid. So just like some types of metal, like the coppers, when we have a metal, so which is like something like, maybe you have like a cube there, then you have many copper atoms. Yeah, you have any atoms there. And then, as you know, in the chemistry class, you know the electron on the outer sphere are free to move, so that the electron can go from here to there, even though the nucleus cannot move. The nucleus can only oscillate around that position, but the electron can move freely. So those electron on the outer sphere is called the free electrons, here, free electrons, and there are few free electrons in a conductor. None, but just few of free electrons in the non-conductor or the isolator. And so we have a charged particles. So it tells you why we have charge, why we have a positive charge or negative charge, because some of the atom can have one additional charge, additional electrons, or lose some electrons. And here it called the induced charge. Here it says a neutral copper rod is electrically isolated from its surrounding by being suspended on a non-conducting thread. Okay, so just look at here. You can just look at here. So this is a copper. We don't have a glass, or we don't have a glass rod here. We have a copper rod. But actually, it is originally neutral, electrically neutral. It don't have any excess charge. And the next step is we try to rub the plastic rod, so it has a negative charge here. If we place this plastic rod close to this neutral copper, then it will induce some charges in the two ends, because this is negative charge and this is isolator. This plastic rod is isolator. So the charge here cannot move, cannot go away. But here this is a conductor, so that the electron will be repelled by this charged plastic rod. So the electron will go to the other side. So it will induce negative charge in this end, and the remaining, because the charge is conserved, so the total charge should be 0. So as much as we have a negative charge on this end, we should have positive charge on the end close to this plastic rod. So we have a positive charge here, and of course the total charge, when you add them together, it should be 0. But this is called the induced charge. 应该是感应电荷啊，感应电荷。Here, yeah. I don't repeat it here. Just explain. Okay. So here, this is the definition of the charge. But this definition is quite. Usually, when we try to define something, usually you will write it as a Q. Charge is Q. Usually, you write it as Q equals something. This is a normal way to write a definition, because it is straightforward. But here is not the case. Here we'll have this dq dt, take the derivative of the charge with respect to time, which is the current. So this is the current. So this is the charge. So this is the charge amount. The change of the charge with respect to time is actually the current. Or in other words, you can say if you have a moving charge, that is actually the current. If you have moving charge, then this is actually the current. So actually this is the dq dt. So the charge, the change of the charge amount in a unit time is the current. And so in this clause, the SI unit, and of course in engineering, well, the SI unit are really, really important. So the SI unit for the charge is Coulomb, the Coulomb. In this chapter, you mainly learn the Coulombs Law. So actually, Coulomb is used to memorize him, and then call, yeah. So the charge, the SI unit of the charge is called the Coulomb, and the SI unit for the current is ampere. Is ampere. So I equals dq dt, or you can understand it as a delta q delta t. So this has a SI unit of ampere. This has a SI unit of Coulomb. Time has a SI unit of s. So actually it is not quite correct to write it like this, but yeah, you can simply consider like this. Usually we will not write it like this. This is not so rigorous to write like this. But when you do something in the exam, you forgot the SI unit, you can try to write something like this to remember yourself. So usually we try to check it like this. Ampere is actually Coulomb per second. Yeah. So this is the definition of charge. And actually, for the current, it has direction, but actually it is not a vector. It is not a vector. So I think in high school you also learn the concept of vector, which is something like a vector has a magnitude and also the direction. So something like like this. Maybe a displacement. Displacement is a kind of vector. You move it from here to there, and yeah, maybe you can move it from here to there. They are vectors. But actually the current, it has direction, but it is not a vector. So you need to remember this concept. And the SI unit are very important, because in the quiz or exam, when you have the wrong SI unit, then each one worth 1 point in the quiz or exam. So make sure you can remember some of the SI unit. But actually the formula I will provide some in the quiz and exam. Usually I will upload it to the Moodle before the quiz or exam, so that you will know what I provide to you. You don't need to remember something, but for the SI unit, you still need to remember. Okay, so this is the main part of this chapter, which is the Coulombs Law, although I believe you should have learned it in high school. But yeah, we still need to go through it. So it says the Coulombs law describes the electrostatic force, or the electric force, between two charged particles. So if the particles have charge Q1 and Q2, so you have a Q1, Q2 here, are separate by distance r. So this is the distance r. And are at rest. This is a assumption, because here it is about the electrostatics. 静电学。We usually assume that the initial condition is like the particle doesn't move at all, and we only calculate the force at that moment. And sometimes later, actually there will be some force acting on this charged particle, and you know the Newton's law of motion, Newton's second law of motion, you know F equals ma. Then if there is some force acting on this particle, it will try to accelerate it in this direction. So at the next moment, then everything change. So for the electrostatics, you just make the assumption that originally they are at rest, and then or moving very very slow relative to each other. Yeah, then the magnitude like that. Otherwise, we need to consider the relativistic effect, which will be really really complicated. Okay, so relatively, the magnitude of the force acting on each due to other is given by this equation. Yeah, it is like F is a vector. F is a vector, the force acting on the charges, and then this 1/4 pi epsilon naught is a constant. We will use this constant really really often, I think, in the whole semester. So 1/4 pi epsilon naught. We usually call this one K. This one. This term we will just call it K here. K is actually 8.99 times 10 to the 9th power, and then with this SI units. Usually I don't remember. In the exam or quiz, I will just provide it to you. You don't really need to remember the numbers. But actually, I already remember it because I already teach this course for several years. So this is K, which is 1/4 pi epsilon naught. Usually they will appear for the whole term like this. Sometimes it will appear independently. This is called epsilon naught, which is 8.85 times 10 to the minus 12 power with this SI unit. And this one, epsilon naught, is called the permittivity constant. I forgot the Chinese. Permittivity constant. In the magnetism, we will have another one called the mu naught. Mu naught, which is called the permeability constant. Yeah, this one, it will also appear like mu naught over 4 pi. So we still have this 4 pi here, and this one is actually 1 times 10 to minus 7. I forgot the SI unit, but I remember number. And here we'll also see the duality. For some of the equation you learn in electrostatics and some of the equation you learn in magnetism, sometimes you only change epsilon to mu naught, epsilon naught to 1/mu naught, and then you change E to B. It will be pretty much like that, and then you get the duality between the formula in electrostatics and magnetism. I will remember you when it appears, but yeah, I just remember this point here. But yeah, maybe you don't really understand why it be like that. But yeah, later on you will see more example about this stuff. Okay, just go back to this equation. This is the constant. This is the constant K, and then here we have Q1 times Q2 over R squared. So I think you should have already learned this Coulombs Law in high school. Okay, but actually this equation is written in the vector form. It's written in the vector form. This is the vector, so the right side should also be a vector. Maybe you in high school, or usually we will just use it like F equals 1/4 pi epsilon naught times Q1 Q2 over R squared, or Sometimes I just write it like k times a q1 q2 over r squared. So this is a scalar form, this is the vector form. And so this is our hat. Our hat is a unit vector. When you see a vector with an arrow, this is a normal vector. This is a not normal vector. It's a not this normal is that not that normal. Normal is normal, but yeah, normal has another meaning. Means orthogonal. But yeah, here this normal doesn't mean the orthogonal. It's a usual vector indicated by this arrow, but this sign means this is a unit vector, which means that the magnitude of this vector is 1. The magnitude of this unit vector is 1. Okay, so how to define this unit vector? So for this case, if we have q2, q1, we try to find the force acting on q1 due to q2. So this is the original point. This is the original point because it tried to generate some force acting on this q1 charge. Okay, so in this case, this is the original point. This is the r-axis. This is the r-axis. So our hat should point to this direction. Our hat should point to this direction for q1. This one is for q1. If we consider the force acting on q2 due to q1, then q1 should be the original point. Q1 should be the original point, and then the r-axis should point to this direction, and then the r hat should point to this direction also, and this r hat is for q2. So this is the punchline of this equation. You can just use this one to express the direction of the forces, and also it also includes the polarity of the charge. Maybe I can just talk about it here. So the punchline of this equation is that it also considers the polarity of q1 and q2. So we have altogether 3 cases. Actually, you may say there are 4 cases, but actually if it is a positive, negative, negative, positive, they are actually the same. So we don't really separate these 2 into a positive, negative, negative, positive. We just merge it to 1. Okay, so here it says the electrostatic force vector acting on a charged particle due to a second charged particle is either directly toward the second particle or directly away from it. Okay, so just now we mentioned that the R hat for the right one point to the right side, the R hat for the left one point to the left side. Okay, so the first case is Q1, Q2 are all positive. Q1 and Q2 are all positive. So here, K is positive, R squared is also positive. And if Q1 and Q2 are also positive, then the whole term will be positive. The whole term will be positive for the first case. For the first case, which means that the force should have the same direction as the unit vector, which means that this is the force. This is the force acting on this charge. This is the force acting on this charge, which are the same, which has the same direction as the unit vector according to them. So this is the first case. For the second case, both of them are negative. Both of them are negative. K is positive. R squared is positive. negative times negative is positive. So the whole term is still positive. So for the case B, which is actually the same. So the force pointing to the right side for the right particle and the left side for the left particle. So which means that for both cases, these two charges repel each other. So for this case, positive, positive, negative, negative, which means that if they have same polarity of charges, then they will repel each other. And for the case C, one is positive, one is negative. So K is positive, R squared is positive. Positive times negative, or negative times positive is negative. So for case C, the polarity of this term is negative. So this force should have an opposite direction as the unit vector, which means that this is our head, this is our head. The force should point to the other way around. In this case, these two charges with the opposite sign attract each other. Okay. So this is a simple case about how to determine the force for two charged particles. Maybe let's have a 15 minutes break.